Welcome to the deep dive. We're looking at some source material you brought in today, focusing on equations and inequations.
That's right, foundational stuff in math. Definitions, properties, how to solve them.
And our mission, as always, is to sort of cut through the noise, pull out the essential takeaways, so you can really grasp these concepts quickly and know what your sources are actually saying.
Exactly. Get you up to speed efficiently.
Okay, let's dive in. Equations first. Your sources define these as, well, statements where two things are equal, right?
Precisely. Think of a balance scale. The expression on one side equals the expression on the other. Like $3 plus 2 equals by 77. That's an equation. It's a claim of equality.
And solving it means finding the value for that variable, the x or whatever, that makes the scale actually balance, makes the statement true.
Yeah, exactly. Like in a simpler one, $6 plus 2 is equals to 6. The only number that works for x is 4. That's the solution. It makes the equation true.
Right, and the sources emphasize this core principle. You can do the same thing, add, subtract, multiply, divide to both sides, and the equality holds, as long as you're not dividing by 0, of course.
That's the absolute bedrock. Keep the balance. If you add 5 to one side, you have to add 5 to the other. It always stays equal.
Okay, but then the source talks about this shortcut method, transposition, just moving terms around. How does that fit?
Yeah. It looks like just moving things, but it's really, just a faster way to think about applying that main rule.
Faster how?
Well, instead of saying I need to subtract 3 from both sides in, say, 60Ls plus 3 equals to 6L, transposition lets you think of just moving the plus 3 over the equal sign.
And it becomes a 9 of 3 on the other side, so 6L is equals 633.
Exactly. Moving a positive term makes it negative. Moving a negative term makes it positive.
And for multiplication and division?
Same idea, just the inverse operation. If it's 3 by 6, the 3s is multiplying, so you move it over and it divides. 6 is 3 3ths.
And if it was 6 3's, you'd move the 3x and it multiplies. 6x equals 6 times 3.
You got it. It's just a handy way to visualize keeping that balance while isolating the variable. Makes solving quicker.
Okay, that makes sense for equations, finding that one point of balance. But now inequations, these are different, right? They're about inequality.
Right. We're talking less than, greater than, less than, or equal to, greater than, or equal to. We're often looking for a whole range of values, not just one specific number.
And the source brings up two concepts here that seem really important for inequations. The replacement set and the solution set.
Oh, absolutely crucial. The replacement set is basically the universe of numbers you're allowed to pick from for your variable.
Yeah.
Is it just whole numbers, integers, all real numbers?
That context matters.
Hugely. Because the solution set is then the group of numbers from that replacement set that actually make the inequation true.
Can you give an example?
Sure. Take $500. If your replacement set is natural numbers 1, 2, 3, your solution set is 1, 2, 3, 4. But if your replacement set is whole numbers 0, 1, 2, the solution set becomes 0, 1, 2, 3, 4. See, the allowed starting pool changes the possible answers.
Got it. Constraint first, then the solution within that constraint. Now, there's a really tricky rule mentioned for inequations, something about negative numbers.
Yes, this is the big one. The major difference from equations. When you multiply or divide both sides of an inequation by a negative number, you have to reverse the direction of the inequality sign. Less than becomes greater than. Greater than or equal to becomes less than or equal to.
Whoa, okay. Why? That seems counterintuitive compared to equations.
Think about the number line. Let's say $2 3 to 3. That's true. Multiply both sides by -1. You get -2 and -3.
Right.
But is -2 less than -3? No, it's greater than -3. It's further to the right on the number line. So $2 -33. Multiplying by the negative flipped their relationship.
So the operation reverses their order on the number line.
Exactly. So if you have, like the source says, 3x seems 12/2, and you divide both sides by -3.
You have to flip the sign.
You must. It becomes 6 by $4. Forgetting that flip is probably the most common error.
That's a critical takeaway. And the source also briefly notes you can show these solution sets on a number line.
Yeah, visually representing that range of answers.
Sure.
Useful tool.
Okay, let's quickly recap then. Equations are about finding that specific point of balance. Transposition is a useful shortcut based on keeping things equal.
And inequations are about finding a range of values, heavily dependent on the starting pool of numbers, the replacement set.
And the absolute key rule for inequations, flip that sign if you multiply or divide by a negative number.
Don't forget it.
So thinking about this for you, the listener, noting how the approach changes. Equations seek precision, that single point. Inequations deal with ranges, possibilities defined by constraints.
Yeah, and understanding how a simple rule change, like that negative number flip, totally alters the potential outcome is huge.
It makes you think, doesn't it? How often, maybe not just in math, do the initial constraints, the replacement set, and the specific rules of manipulation drastically shape the solutions you can find? Worth going back to your sources with that lens.